Okay, so good afternoon, everyone. We're really happy to have Yuxun give the HIT seminar today. Yuxun is a postdoc in our group. He recently joined us. He got his PhD from the University of Maryland a couple of months ago, and he was visiting us for the last 2-3 months. 4 months, okay. But he's now formally a postdoc in our group. And he's a member of the quark tomography collaboration. And part of today's work is related to the goals of this collaboration. And so he's going to tell us about gravitational form factors through near threshold heavy proton reproduction. Please.
Yeah, well, thank you very much for the nice introductions. The mic is right here, I guess.
Yeah, I think so.
Yeah.
But you can ignore the remote.
Yeah, it's fine.
Thanks for a nice introduction. And again, I will talk about the probing the gravitational form factors from special JLab production. This talk is based on several publications with my collaborators. You see here. So here's the outline of the talk. I will start with a rather brief introduction about nucleon structures and gravitational form factors for those of you who haven't heard of it. And I will briefly talk about the quarkonium production and how we can use it to probe the gluonic structure in the nucleon. And next, I will talk a little bit about a little bit technical stuff that is how we can extract the gravitational form factor using the so-called Compton form factors that I will introduce later. And then I will use this threshold JLab production as an example to illustrate how we can extract or constrain the gravitational form factors of proton as an example. And in the end, there's of course a summary and outlook. So, let's start with something we all know, right? We all know that the original mass is highly non-trivial in quantum chromodynamics, mostly because the nucleon mass is largely from strong interactions. So if you look at the mass of a proton, you'll find that the mass of the constituent particle is really small compared to the mass of a proton. So that tells us many of them are actually from interactions. And here's a calculation on lattice QCDs, actually by the chi-QCD group. You can see that there are 4 terms here. The quark masses only take about 10% of the proton mass in the budget, and the quark energy, the dynamic energy, is actually 30%, whereas the gluonic energy is about 40%. And there's a very special term called the QCD trace anomaly term that takes about 23%, which is theoretically 25% exactly a quarter. So those terms are not just made up. You can actually look at them in the QCD Hamiltonian, which is just the zero component in moment tensor. That is, if you decompose QCD Hamiltonian, you'll find out exactly that there's 4 terms corresponding to each of them above.
But isn't there interaction between gluons and quarks in the QCD Hamiltonian? So how do you budget that?
The interaction part is, yes, it's there, but it's actually.
So on one side, where in your budget is it the quark energy, is it the gluon energy, or?
Then
Probably some feedback between the two.
Well,
it's
maybe I sound bureaucratic, but I'm getting used to being back at Berkeley, so I want to get my spreadsheet right. So
there is. I kind of forgot what is the gauge choices, but there is definitely some correlation between separating the quark energy from the gluonic contribution, but they can be defined on optical level. Probably choosing a fixed a third gauge, and I'm not exactly sure of it. Can't recall that. Now, what's kind of special is about this is actually this quantum anomalous energy, which is a trace anomaly here, because we know that if there's no trace anomaly in the chiral limit, the theory is the scaleless, so you should be getting everything else to be 0. But because of this non-zero quantum anomalous energy term, you actually set a scale for 3 other terms. That is why you see all these terms are not close to 0. They're actually very non-trivial, proportional to none of the QCDs. So that's mysterious of the original mass. And it's actually, I remember that the very, I need to type this on my, I don't see everything. One of the first, I think this is the very first talk that I attended, which was on the topics of original mass by Professor Frank Wilczek, which is exactly 9 years from now. So it's actually 2014, October 10, in case you don't see it. So it's actually a very interesting coincidence that after 9 years, I'll be talking about this very subject myself. And I was a first-year undergrad, so I probably didn't know anything what he's talking about. Okay, so rather counterintuitively, the mass structure of the microscopic particles like proton is not easily studied. And this can be compared to, for instance, the charge structure of the proton. We measure the charge of a proton more than 100 years ago by the famous Newton oil drop experiment. We measure the actual charge. For that, we know the proton charge. But 100 years after that, we still don't know much about the charge radius. Well, we know much about that. But there's still inconsistency here, as you can see. That is the famous proton charge radius puzzle. Actually, I saw this pretty nice plot by Evangeline at the spin conference last month at Duke. And for the gravitational structure, for mass structure, we're doing even worse because doing electromagnetic scattering is relatively easy, whereas doing gravitational scattering with nucleon is almost impossible. So apparently, at this point, it's hard to get just a single point we had on the left-hand side. Therefore, if you want to measure the mass structure of a nucleon like this, the first thing we need to think is what is the ruler? How do we measure it? What is the tool we study that? So the property, the quantity we consider here is actually the energy moment tensor form factors. It's kind of intuitive because if you're interested in the charge form factor, if you're interested in the charge structure, you care about the charge form factors, and if you care about mechanical properties of the nucleon, you think of the energy moment tensor and its form factors. So you can show that the matrix element of the energy moment tensor form factors can be written into 4 different terms corresponding to different Dirac structure, A, B, C, and C bars. And you can actually assign different physical meaning to that. For instance, the A form factor is actually correspond to a momentum because if you take a forward limit, A is just the momentum fraction of the quarks and gluons. And the B here is actually can combine with A, that gives you the nucleon spin. So this thing, if you combine the quarks and gluons together, it gives you exactly a half, which stands for the proton spin. The C form factors, if you want to interpret it, there's some debate on this, but you can basically interpret in terms of the stress form factors, which kind of characterizes the pressures and the shear forces in the nucleon. Again, there's some debate, but roughly that's the case. And the C bar form factor is a little bit more mysterious. It's proportional to G mu nu, kind of like the dark energy. And also it's kind of less mysterious as dark energy because it doesn't have a very simple mechanical interpretation. If you take a forward limit, the B and C actually vanishes. So only C and A survive. So the C bar form factor actually contribute to a quark and gluon energy. But if you combine the quark and gluon together, it has to vanish because this G mu nu term doesn't conserve any moment tensor. So if you add the quark and gluon together, this term has to vanish. So you can see that it kind of corresponds to some non-trivial redistribution of quark and gluon energy. And when you combine them, it disappears. We won't talk too much about the C bar, but it's of course very interesting.
Usually it's nonsense. I mean, it's not. It's nonsense to separate quark and gluon mass just to combine them together. This is physical observable. Separated, not physical observable. Can I say that?
There are, yes. In general, you cannot separate quark from gluon, but there are gauging. This is very similar to the previous question. That there are ways you can separate them in a rather gauge invariant way. That is, you combine part of the dynamic part with there's the K part, the covariant derivative. Combine part of the dynamic part with the gluon part to form some kind of covariant derivative, so you still have some kind of gauge invariant decomposition. But in general, very specifically, there could be scheme dependent. Yes. So first, understanding the mass and the spin structure of the nucleon is one of the fundamental problems we want to answer here. Actually, if you look at the scientific report of ESC, the question how does the mass and the spin of the nucleon arises is listed here as one of the important question we need to answer, but apparently you cannot directly measure the gravitational form factor with EIC because it's electron ion collider. It's not a graviton ion collider, right, which is beyond what I can imagine. But apparently with electron ion collision, you cannot probe the gravitational form factor directly. That's the dilemma here. So the question is, how do we approach those gravitational form factors, say with EIC or any kinds of.
So I have a naive question. This first, how does the mass of the nucleon arise? How does one answer this question? I mean, there is already this budget from the lattice. What else?
Yeah, that's a very interesting thing to discuss. Actually, probably beyond this work. That is, we discussed that the quantum anomalous energy is actually very is basically simple for the break of the scaling symmetries. That is, that for instance, you can consider these. For instance, you can take the trace of the moment tensor that corresponds to a scalar contribution. That is a quantum anomalous energy we have to factor in. And you got the scalar form factors. The idea is that why in the scalar form factor is non-zero in the nucleon instead of outside, because we know that if it's zero, there's no nuclear mass. But so if you take the Fourier, for instance, in classic picture, you can take the Fourier transform of the scalar form factors. They can be considered as the classic interpretation of the scalar energy distribution inside the nucleon. You'll see that decays away as you go outside the nucleon. That probably gave you some thought of how the mass has been generated. That's one of the general pictures. One example pictures of how we can how we can study that with like gravitational form factors. But of course, in general, they are much more complicated physics behind that, which is beyond what we can beyond what we can do with simply just the gravitational form factors. We need more information, for instance, in the X dependence. That's actually what I will talk about here. That is, we know that the electron line collider cannot directly probe a gravitational form factor. So the alternative way or the detour we took is that instead of directly measuring the nucleon as a whole, which you need to do gravitational scattering, we just knock out a parton at a time. For that, you don't necessarily need to do gravitational scattering. You can use, for instance, in this case, the photon collision. So you emit, for instance, a virtual photon collide with the quarks, and the quark gets back to a nucleon. So it's kind of like if you look at the matrix element here, it's kind of like just the quark form factors with non-zero momentum transfers. And this point here is actually called a generalized parton distribution, because it's a generalization of a parton distribution to a non-zero momentum transfer. So if you take delta to 0, that's just parton distribution. So GPD here is just the distribution that unifies the parton distribution and the form factors, as you can see. And since the delta is a full vector, we typically project into different scalars just to make it easy to handle. So the C here is called a skewness parameters, which is the longitudinal projection of the momentum transfer, and the T just for the moment transfer square. That is like the Q square is that in the form factors. One thought here is that you might want to interpret this, since I talked about this, you might want to interpret the GPD as just the tonic form factors, right? That's just what I said, but it's actually a bit more non-trivial than that because of the skewness parameters. If there is no longitudinal momentum transfer, of course the parton is moving, you give it a recoil, that's the partonic form factors. But if you have longitudinal momentum transfer during this recoil, the parton actually changes longitudinal momentum. And to make things worse, its positive momentum can go to negative if c is larger than x, right? So if you have a collision and after that your momentum becomes x minus c, then you change its sign. And that completely messed up with the interpretation of partonic form factors of GPDs. But you can do that at zero skewness. That is, when the momentum transfer is complete in the transverse direction and the skewness is 0, in that case, you can simply interpret as partonic form factors. And actually, there's some benefit of doing that. So with that said, actually, we can get back to the question, how can we access the gravitational form factors? That is, once we measure the GPDs, which is a very non-trivial and hard task themselves, but it's probably more realistic than doing gravitational scattering. Once we have them, you can actually combine all the contribution from all the partons and get back to the gravitational form factors. This is simple, right? So for instance, you can actually sum over the GPDs, d over dx is the sum over partons. You sum over all partons of each GPD, you get back to the direct form factors, and there's another GPD called E, and you can sum over them to get the Pauli form factors. And the same thing can be done for the gravitational form factors. That is, instead of just sum over them, you take the moments, x is also momentum. So you can take the moment or the momentum as a weight. So if you are summing over all partons with the momentum as a weight, you are essentially getting the momentum flow of the momentum structure of the whole nucleon. So if you take the first moment, obviously you will get back to the gravitational form factors, and indeed you will get the A and C form factors that we showed in the previous slides. And the same thing for the E, you will be getting the B form factors, which is crucial for studying the spin structure of the nucleon, and also C form factors here. And in principle, you can take higher moments, then generate more form factors. In that way, GPD can be considered as the generators of the form factors.
So why don't I see a tensor structure in these equations for the gravitational form factor?
Because this is linear projection, so we only project the highest.
A tensor is a tensor, right? And so why don't I have an xy or xi type structure, just linear x? Is there a simple explanation? I mean, same for the charge form factor. Well, but for the gravitation, I would assume they have at least two arguments to make a tensor.
Yeah, this is a leading interest projection, which means that they project the highest spin contribution, which is that's the reason you don't see the C bar here, because the C bar is a higher twist of operators. So this X here is basically saying that you only take the longitudinal momentum of the partons. If you want to take the transverse momentum of a parton, you will see other tensor structure and produce other gravitational form factors. But that's here we only show those two GPT are the only two leading to SGPT, so they only project the leading to its part. You can consider as a one projection of the tensor structures.
Oh, so it's a projection, it's not the tensor itself.
Yeah, this is it's a scalar function, right? It must be some projection.
All right. Okay. Thank you.
Another interesting thing you can do with GPT is actually associated to the partonic form factor interpretation. That is, once you have a form factor, you can in principle perform a Fourier transform that gives you the semi-classic picture in the coordinate space. And as we said, that the GPT only has this partonic form factor interpretation in the zero skewness limit. As a result, you can actually perform a Fourier transform in zero skewness limit. That is, when the momentum transfer is complete in the transverse directions, you can just do a Fourier transform in transfer space that basically localize quarks in transfer space. So this rho here is it depends on the parton momentum fraction x and also the transfer space b. So you can consider that as the parton moving in the z direction with momentum fraction x and localized in the transfer space. So this is a very nice picture. You can use this to generate all kinds of observable beyond just the gravitational form factors. So that's interesting things you can do with GPT, and how that's also another way how we can access gravitational form factors from the electron amplifiers.
I have another question. Is this relationship between moments of the GPDs and the gravitational form factors, is it obvious? Like in the first or second slide, you show the energy momentum tensor, and then you decompose it into different Lorentz structures, and you define this A, B, C, C bar. And now you're making a connection with GPDs, which in my mind have some operator definition. So how is the connection seems like very magical, right?
Yeah, it's actually very obvious in the operator level. That is this is like the psi bar gamma mu d mu here. That's the energy momentum tensor. And the GPD itself is like Lycombe distribution, which is psi bar gamma mu psi. If you perform a Taylor expansion, the leading order is psi bar d mu gamma nu, and that gives you all this.
So I think if I think of this energy momentum tensor in terms of operator, then I can see okay.
Yeah, it's a basically non-local operator expanded into a series of local operators, and each of them is form factors.
Okay. Okay. Thank you. So that's why you need to. That's why you need to get the moments, right?
Yeah, x is basically one derivative.
So
if you don't take any derivative, that's just the current versus.
Yes. Okay.
So next, I want to talk about the quarkonium production. It's actually not a new idea that we can use this quarkonium production to probe the gluonic structure. The semi-classic picture you can think of that is if you place a dipole in the electric field, you can basically use a dipole interaction with the electric field to measure the electric field. That is a Stark effect. And here we're basically doing this analog in QCD. That is, if we place a very small dipole in the proton, then this their interaction basically measures the local E distribution in the which is a color E field in the proton. Of course, to have that, you want to make sure that the charge, the dipole size is much smaller than the size of the proton. So in this sense, we prefer very heavy proton, very heavy dipole, so that its size is much smaller than the proton. So in this case, we can use this very heavy quarkonium as a color dipole to probe the gluonic structure in the nucleon. So ideally, we want to have something like that. So you probably want to say, let's have an elastic scattering of J psi of the nucleon, which is probably more realistic than doing gravitational scattering with the nucleon, but still we don't have very well J psi beam. So that's still beyond we can go. So in real life, we just have this photo production and electric production instead. So just want to make sure that you have J psi in the final state. That is the compromise here.
So this interaction component is like a non-relative to the expansion of the quarkonium system.
Mm-hmm.
So what's if you have relativity correction, what will be that? So you will have more operator associated.
Yeah. This received multiple. So first, once you are moving, you also couple to magnetic parts, and the operator themselves also has negative refraction, so it becomes very common. This is only the velocity equals 0 approximation. That's leading order expansion in arches. But yeah, so in the same picture it also exists in the GPT framework. That is, if you have, for instance, we consider here the electron production of the Gibbs-type particle. In this case, if you have a virtual photon, it first split into a quarkonium pair, and by exchange of two gluons between them, you eventually form a boundary of Gibbs-type particles. So this is basically a CC bar here. On the other hand, you could also have this type of diagram contribution from the quark side. That is, you first find an intrinsic quarkonium in the GPDs, in the protons, and this intrinsic quarkonium exchange with a virtual photon with an electron beam, and essentially turns into a meson in the final state. And obviously, this is what we want to study the gluonic structure. So that's another reason we prefer heavy quarkonium production, because we generally believe that it's less likely that you will find a pair of CC bar in the proton compared to if you find a UU bar, which is much more common. So in the heavy quarkonium production, we typically believe that the first type of diagram will dominate in this process. And this means that we want to produce very high energy, very heavy high energy particle in the final state that actually requires a lot of energies. And that's essentially why we need a.
Isn't that people recently said that they found actually the intrinsic charm inside the proton is not zero?
Yes, I kind of read the paper. And they use some kind of fancy machine learning thing, and they argue that it's not.
No, this is measured. I mean, they're telling that they're trying to measure it, right?
Yeah, I think the argument is that it's not. They cannot exclude it from existing. But it's like it's non-zero. It's consistent with non-zero basically, but they don't have very sizable measurements. So. Yeah, that could be the case, but I would imagine that generally it's still a small number, even if it's non-zero. I don't know.
Do I need electron scattering? Can I do this with photons from an ion beam, like proton nucleus scattering at the LHC? If I could do it, I'm not sure that I can do this there.
Yeah, I think in that case, the complex part is this part, not this part. So if that, you're talking about quasi-real production?
Exactly, right?
Yeah.
I come with this huge photon field from the nucleus and hit a proton.
Yeah. Yeah, I think that's interesting to think. I mean, you just need to replace that with
maybe I don't need the EIC, that's my question, right? I can get it done before the EIC starts.
Oh yeah, yeah.
But you have to, then you're talking about peripheral interaction, right?
Sure.
That's what
Then
far
you are
away
doing the GPT of hydrogen nucleus.
Yeah.
Instead of proton.
No, but you can
there's a
probe
TA
the
too.
TA, and then the
TA.
ion is the photon source, and then you probe the beam.
Oh, yeah, on the other side.
Yeah.
Yeah, I think in ideal case, you have a quasi-real production and you have a proton here. If you can separate them from other signal, in principle, they're the same thing.
Yeah. So
The thing is that maybe the majority for peripheral interaction, the cross section for highly virtual photon is that still big enough? Now most of the photon is almost
real.
on shell,
yeah.
a real photon. But this is in order to produce this bar, the photon is pretty virtual.
No, it doesn't
don't
come
need
to
it.
the
You know?
You just need enough momentum transfer in the
You just need energy.
and I have lots of photons.
Yeah, not to know. So that will be another talk by Farid.
Okay.
He did some calculation, right?
Oh yeah.
Yeah.
So a question here. So speaking about UPCs, there was this paper by a group in Jyväskylä that they claim that the next to leading order, there is a large quark contribution, right? It's actually dominant, right? It dominates over gluons.
It's the same magnitude, I think. Order of magnitude is the same. So
Yeah, but I think at mid rapidity it was
that's true.
dominated by quarks. So yes, I don't know if that was on the context of GPDs or not.
Yes.
It was in the context of GPDs. Okay. So what's your perspective here on that?
Yeah, in principle, what the size of zero is should be about the same thing here, but yeah, their work has a lot of scale dependency in there, so you cannot really. They don't have a very large Q square, so in the result they show a large part contribution with large uncertainty, and they choose a scale to do that. So, but that general feature I think is probably the same here. That is, you might have a significant extreme or correction. Okay.
Does that screw up with this extraction of the quark back? If they were to be correct.
Yeah. If you're talking about the scenario where next order is larger than linear order, that would definitely the linear order extraction. So yeah, actually, I haven't get to my conclusion that next order is important,
Okay.
as I will.
Let me just add a comment. So that's part of the reason why we have Yan in here. So he will be here like 3 weeks or whatever. So he's doing this for UPC too. And
Just one.
in small x.
Yeah.
So that particular calculation is for the small x.
But this NLO computation was not with the small x. Janis was, but this one that I'm mentioning.
But the key factor why that beats is because of small x. Okay. Because they have kind of a divergence if you really go to very small x. So that means they have a BFK evolution for that GPDs. But here, I mean, for this ratio, you don't have.
Yeah, this is a larger, not very large, but larger X region, so it could be different, but the size is generally the picture is generally. So yeah, that's essentially for instance, what we can do with EIC. This is the extrapolated plot based on this exclusive J site production here, and this is kind of the transverse distribution of the gluon based on what you can get from a GPD. Of course, this is not actually from GPDs because I will talk about it. This is actually from constant form factors. But that's basically what you can do is this exclusive J site production with at EIC. And of course, EIC is very far away from us in 10 years, and it takes even more time for it to operate and take more data. So obviously, we don't want to wait 14 years or more to really think of what we can do with the gluonic structure that starting then. So the idea is that can we do this study of gluonic structure at low energy, and there has been this very nice measurements by the GLUX collaboration rather recently, and this has raised a lot of interest in the community that is can we study this threshold production, which requires much less energies, and also probably have sensitivity to gluonic structures. And that's what we're doing here. So here, I will not go into the details of how of this calculation, but basically we study this process in this GPD framework, and unsurprisingly, it's very similar procedure as you would have in the collinear case. And so we show that to leading order, you basically can factorize this process with GPDs, and you actually get the same amplitude as you would imagine. This is the same Feynman diagram as collinear production process. So it's the same amplitude, but the kinematic is very different, as we just discussed. The major difference is that the momentum transfer in this case is large, or also in this case, the skewness is large. The idea is that you produce a very heavy vector meson in the final state from a massless photon. Near the threshold, you need to have very large momentum transfer between them. So that's the basic idea, and this is basically the cross-section formula. If you're familiar with exclusive production, this is the same formula that you would see for instance, DECS or DVMP. This is just the general kind of things you get from this kind of diagrams. And those amplitude here, H and E, that called the Compton form factors, because this is like a Compton scattering in the quark case. So this is called, we can call it gluonic Compton form factors. They are basically the amplitude given by these diagrams. And so in principle, you can study this process to extract the Compton form factors, which is amplitude here. However, there is a well-known obstacle that is called inverse problem. The idea is that we talk about this partonic form factors interpretation of GPDs, but actually to measure them in exclusive process is not easy, and it's kind of a fundamental. That is, we want to have an exclusive process, so we want to keep the proton intact in the final states. And to do that, we cannot really measure the momentum of a parton. If you measure it, it comes on show, and you will basically break the proton into pieces. So to really have an intact proton in the final state, you need to make sure you form a loop. You first measure it and you get back to a proton. So you got a proton intact in the final state. And in this process, the parton momentum will not be explicitly measured, because you can see there is a momentum flow, and you basically need to integrate over all the parton with different momentum. That's the general features in exclusive production. And as a result, if you look at this amplitude, which is this Compton form factors, it's going to be giving us an integral over x with the hard scattering coefficient depending on x, and the GPD depending on x. So this dx again stands for summing overall partons of different momentum, because you're summing over this loop. And as a result, if you measure the amplitude, the x dependency in that sense is basically lost in GPD. So you cannot use this amplitude to really constrain the x dependence of a parton momentum. And this is this kind of famous shadow GPD defined based on this. That is, if you look at this equation, and the two lines are basically two different GPDs. So you insert these two different lines, the solid and dashed line, into the right-hand side. They produce the same amplitude on the left-hand side, which is obvious because not obvious, but which is obviously possible because this is the integral.
So the left-hand side I measure, and the right-hand side I want. Okay.
Yes. Yeah.
Thank you.
Yeah. We expect to extract this from this.
Yeah.
You got two possible solutions, or actually infinite possible solutions.
Deep learning.
Deep learning, yeah, that's right.
So this is kind of the dilemma we're faced with. We want to go this way. We want to have a GPD so that we can measure constant form factor, the gravitational form factor, which is basically managed by taking the moments. But in reality, what we measure is a GPD. You take convolution with the Wilson coefficient and goes to this way. And obviously, we cannot go backwards. That's the famous inverse problem. You don't get a unique solution of this. And the question thing is that okay, maybe we can go instead this way. Can we build a connection between the constant form factors and gravitational form factors? So that's the rather technical part of this talk. That is, can we go from the constant form factor to gravitation? So this is what I just talked about. Let me just briefly recap this. That is, in the case of near-special kinematics, that is, if you want to produce a very massive quarkonium in the final state, you actually need a lot of momentum transfer near the threshold. So you have a massless particle and produce massive particles, and this is the kinematic coverage of that. This is a kinematic diagram. So anything inside this, within this black line, is basically kinematic allowed, and this is the threshold, which is about like the beam. This is the beam energy of a photon, and the y-axis is momentum transfer. So near the threshold, you basically can only have a very limited kinematic coverage because there's only one point you can. And as you get higher and higher energy, the phase space basically opens up. And as you can see that near the threshold, the T is actually rather large, which is -2 here if you cannot rate. And also the skewness, which is longitudinal momentum transfer, is also large. That's just the feature of this heavy quarkonium production. If you have infinite heavy quarkonium produced, the momentum transfer, of course, will be infinite, and the skewness will be 1 correspondingly. So this is a little bit different from what we commonly do in collinear scattering. That is, X and C is typically small, especially if you go to ESC, that's 10 to the minus something. So this large skewness actually helps us in obtaining the gravitational form factors, as we should say. So original argument is rather based on the Taylor expansion. So the idea is that if you look at this Wilson coefficient, let's suppose that C is large enough, it's 1, you can perform the Taylor expansion. That is basically look like this. Nothing complicated. And if C is large, you can basically take the leading terms in Taylor series, so approximate the leading terms, and plug into basically plug into the convolution. For that, you will basically get the moments of GPD like this. And this actually reduced to gravitational form factors. So this is all nice in principle, but the idea is that in real life, the C is always less than 1. That's the kinematic limit. To reach infinite C, you need infinite heavy particle. That is not possible. And this expansion obviously doesn't make sense if you have C less than 1, because your higher order terms is much larger than the lower order terms. So this, if you take this integral, you find that the Taylor series should in principle diverge if X is larger than C, as you see here. And this generally happens because C is less than 1, and X is also always goes from -1 to 1. So instead of saying that, okay, we take the leading term and there's higher contamination, the more serious issue we should consider is that if this expansion will break down, and in essence, all the approximation itself doesn't make sense. So that's of course horrible if that happened. That means you don't talk about next integral correction because everything has integral doesn't make sense anymore. But it takes a little bit of courage to move on. That is, from quantity theory, we know that if you have divergence, usually you can pretend that nothing can happen and keep moving on unless you hit the divergence directly and you need to worry about it. So let's see what we have. If we can do something like that here. That is, we know that this series is going to diverge if X is larger than C, but we still plug everything here. And this is the condition we talked about before. That is, if you take the moments of GPD, it becomes all kinds of form factors, like charge form factor, gravitational form factors. In general, they're called generalized form factors, just typically standing for a bunch of higher spin local operators here. and just plug all of them back into the real part content form factors, you will see this expression. Again, up to this part, everything is kind of exact. That is, there's nothing that we've done wrong, and you will see that it's still got a divergence series because this is less than 1. So if you sum you over to very high orders, this term is going to be infinite. So this is still divergent series. And we want to argue here is that, well, can you actually approximate it just with the first few terms, which sounds very tricky, but there is some magic here. That is, we try some just some past example. Unfortunately, we don't have very good knowledge of GPT, so we want to kind of use actual, say, experiment or exact GPT or theoretical GPT to do this. But we do try some different models, and you can see that those points are already calculated with these models, and those dashed line basically stand for fit, which uses ansatz of A plus B times divided by C squared. That is ansatz suggested by the previous slides over here. So these two undetermined coefficients. So we tried actually two of them with different parameters, and in general they all behave like this. So of course this is not super excited. I mean, it's a line, so it's just plotted. I mean, you can choose different functional form to fit it, and typically there's much more. There's an infinite set of parameters or set of ansatz you can describe it. Just like this is one of my famous quotes from the von Neumann, that is, you can fit an elephant with 4 parameters, and if you have 5 parameters, you can make them wiggle strong. So fitting itself is not that important, but what we want to know here is that can we actually extract physical information from that? Is the question is, can we get back the gravitational form factor from the content form factors? And remember that this is the ansatz we used, and this is the fitted value here. The number doesn't really matter if one rate is minus 0.8, 4.8, and plus 1 for these two coefficients. And the idea is that these two coefficients are actually calculable in terms of all these generalized form factors. And to a leading order, that is, if you ignore all the higher spin operators, you only get gravitational form factors. In that case, those coefficients can be related to the gravitational form factors like this. So this is 2 times this, and this is 8 times this. I didn't make up all the prefactors, they are just there, but I ignore all the higher order terms, that is higher moments. So we can basically, this is the input value we plug in. So AG is just the gluon momentum fraction, which is about 0.4, and the CG is just something which is quantized, which is the reference value of maybe 0.5. And this is what we can read from this plot is, you can see that the AG here, if you take the half, that is 0.5, and the CG here is negative 0.6. So this is not very far away from this. And if you look at the extracted value is about 25% larger than the inputted leading moments. And the idea that in this expression there are actually higher moments. So we only calculate approximately with the leading term. So there's going to be some higher order moment contamination that stands for that account for the extra 25% in this coefficient. This is actually this plus higher moments. So this looks nice, of course. That means.
Sorry, by the higher moments, you mean that those would come with different powers of psi, right?
Oh yeah, that is in each coefficient. This CG here, we approximated, for instance, using the gravitational form factors. But the coefficient CG actually is gravitational form factors plus higher moments plus higher moments plus higher moments. So this is like the x moment. That's the integral, and you can integrate over x squared. That gives higher moments. You can integrate to x to the 4th. That gives you higher moments. Those terms actually contribute to the extra terms here.
But those higher moments also will come accompanied with powers of psi, right? Is that true? From this kind of.
So yes, in general, you can see that there's higher powers of C, but there's also higher powers of C. So those higher moments not. So those higher moments, for instance, you want C to the 4th. That means that you have to be higher moments. But also you can have cancellation, which means the higher moments could contribite to the lower terms. So it's like a triangular kind of process. So this actually contains higher moments. This contains higher moments. And the higher coefficient only contains higher moments. But they're also there in the lower moments. Just that that's general. So all this coefficient, they also have higher moments in them.
So why does it work so well? Just with 2.
The idea is that actually there's no straight proof of that. We do have more heuristic argument in the paper. The idea is that I will go to that side.
Okay.
Yeah, actually, it's right here on the next slide. So the way we understand this is actually in this very interesting concept called asymptotic expansion. It's a little bit unconventional if you're familiar with the just Taylor expansion that basically give you a convergent Taylor series, and the typical feature that we are all familiar with is like if you, this blue dots at the size of each individual terms, and in a convergent series it should always goes lower and lower and typically goes to zero eventually. And if you this orange line is basically their partial sum, and as each term is get lower and lower, the partial sum actually approach the solid line, which is our input value. That's a typical behavior of asymptotic of a convergent series. For asymptotic series, things gets a little bit complicated. That is, at the beginning, it looks like a convergent series, so it goes down as the same as the convergent series. But if you pass through some point, you will start to increase, and this actually keep going up until to infinite. I didn't truncate this series. I truncated here, but if I plot like to 100 moments or 1,000 moments, the size is actually infinite, not some bounded value. So the idea is that if you start to see this partial sum, you still see that because each term goes down at first, you see it goes to some stable value, but eventually because each term goes up, the summation, the partial sum will diverge at all. But you can see that there's a very interesting behavior that is, by the time the term gets its minimum, if you truncate the series, the partial sum actually get a very good approximation of the input value. That's actually understood as a superasymptotic expansion, superasymptotic approximation, which is a very nice feature of asymptotic expansion. So the idea is that yes, it's a divergent series as we argued before, but it's not that bad if you want to just take the first few moments to approximate this analytic result that we measure in the experiment. So,
but the best moment will fluctuate case by case. Different system will define best moments.
Yes, well, that is. So eventually, we are when we assume or we consider this asymptotic expansion, essentially, if you look at this plot, that means we are assuming that the higher moments is somehow suppressed. That is, you don't see this weird fluctuation tail when in the higher moments. Here you see something like this oscillate. That we don't want. And this is closely related to the endpoint constraint. That is, if the GPT has to vanish at x1, like the parton distribution has to vanish at x1, that actually put a non-trivial requirement in the higher moments of PDF. You can make this analog with PDF. That is, if you want to make sure that the PDF vanishes at x1, the higher moments of PDF must vanish in a certain speed so that it doesn't create a non-zero value at x1. And there is a very similar requirement from the endpoint constraint of GPT that also GPT vanishes at x1, and higher moments of all this has to be suppressed. But that's the argument for large GA. You could also argue that there is some non-trivial structure here that say the second moment is anomaly larger than what we expected, or probably even comparable to the first moment. That could be a case, but that would be a very important source of systematics to consider. But in general, we do not expect those higher moments to be significantly larger than low moments. Actually, there are many lattice calculations showing that the higher moments are typically much smaller than lower moments. So we generally don't worry about that, but there is no strong argument saying that cannot. So yeah, that's actually the what I want to talk about in this slide. That is because I don't want to dive into the technical details. That is, this three conditions is basically chained together. It's not like you can prove strictly that the endpoint constraint requires the higher moments to behave like that. But in general, if you want to have endpoint constraint, you have suppression of higher moments that actually correspond to this asymptotic expansion. Those three behavior are actually chained together like this. And also there's a very interesting observation that is about this 25x's, that is our extracted value is always larger than the input value by 25%. And in our study, this is kind of magical, but in our when we try different models and GPT and try different parameters, there's also this kind of 25% exists consistently. And this has something to do with the so-called conformal ratio. That is, if you instead of all the gravitational form factors or other generalized form factors we talk about here are Melling moments, which you take x moments of that. And if you instead of choosing the conformal moments, it seems like the series got a better convergence, and not better convergence, but got a fast convergence because it's not a convergent series, so I shouldn't say that. So the idea is that the first conformal moments is exactly 25% more than the first model moments. So it seems like the first conformal moments is getting a good approximation of real part constant amplitude.
What is the conformal moment?
It's basically the projection with Giegenbauer moments rather than Rowling moments, which is so in real moments you take the integral with x to the powers, and in conformal moments you take it with the Giegenbauer moments of x over c. Yeah. So it's just another way of basically shuffling it's basically a way of shuffling all these moments such that all this contribution were squeezed to the leading terms. But in principle, you can do that, but we don't know which series will do that. But it looks like conformal moments kind of do that job for us. But and the reason is that conformal moments is strictly within the ERDU region. That it strictly vanish at x. So, but yeah, I don't want to dive into all the details, but we can discuss that later. But this is some kind of a conformal moments magic that is explaining 25%. The reason I'm mentioning this is that if you remember that our previous extraction shows that this is exactly 25% more than that. If we take that 25% exists into account by assuming that this is conformal moments, this extraction is actually pretty close to the input value. So it's actually very good improvement, but still in general there will be higher moment contamination. So in the end, I want to talk a little bit about how we can apply this to the real world production data. So I will take the JLab production as an example. So the general framework is pretty straightforward, as I already kind of illustrated. That is, if you can approximate the amplitude, the real part of amplitude using those coefficients are in principle related to the gravitational form factor as we showed, and you can basically utilize those functional form and essentially related all this production data with the gravitational form factor that's encoded in those coefficients. It's just a little bit unfortunately, or that is when we do this utilizes a large C expansion. However, if you look at the experiment, or in general any experiment, you know that most of the events will be in the forward region, which has low momentum transfer. So if you look at this is the kinematic plots. That is this is a very similar plot I showed before, but all the dots are actually stands for one experimental data. That is, you will find that most of data actually has C less than 0.4. And a huge chunk of them has C less than 0.5. And if you want to study the large C region, there are not that many data points. That's a kind of unfortunate like a challenge. That is, we are working in a large C and large T framework, and that's usually where experiment data tends to lack. But anyways, let's just for instance take the C equals larger than 0.5 data, for example, by combining everything we talked about before. We can basically use that to extract the gravitational form factors. That's an illustration of what we can do here. And this is the A form factors here on the left and the C form factor on the right. And you can see that there is a huge difference, right? The A form factor looks very nice, and the C form factor looks really horrible if you want to consider as extraction. And the idea is that this is not a completely independent extraction. As you can imagine, since we only have information for a large T region, it's hard for us to just extract any form factors, because the form factor need a full coverage in the T space. So when we do this extraction, we actually cannot get the lower T region covered very well by the experimental data. And the reason that the HG form factor gets a very good constraint is that we actually impose this gluonic momentum fraction from PDF. We know that the gluonic momentum fraction is about 0.4, so that actually stands for this point over here, and therefore we can use the remaining large T data to constrain its T dependence. That's the reason you got a very good plots over here. That's from actually the forward constraint. But for the CG form factor, obviously we don't have the measurement of CG0 from experiment, and that's the reason that the whole thing kind of blows up. You go to the near forward region when T is small. So and also the coverage in the C is very limited. So that actually limited the statistic a lot. If you have more data, the band will typically be much smaller. But that's what we don't have now. So that's about the gravitational form factors extraction here. So one thing more about talk about is the mass radius. because this has been discussed, for instance, in the recent JLab measurements. What I want to mention is that the proton mass and scalar radii, they're actually closely related to the form factor at zero moment transfer, because just like in the charge radius case, you want to measure charge form factors and take your derivative at zero moment transfer. So all this radii, they are naturally a local quantity that they want to take the zero moment transfer. So that's the same thing here for the mass form factor. So mass form factor are closely related to the derivative of A form factors and the C form factor at t equals 0. And that means that you want to have those information on this form factor at t equals 0. And this is actually not very easily constrained using this framework, because this framework is most applicable in the large T or large C region. So here we show basically the expression. For instance, this is the scalar form factors, and this is a very similar one. There's the mass form factors. This is scalar radius. This one is actually calculated from lattice, and this one is a holographic one, which is very similar to a lattice because they kind of normalize their data according to lattice data. So they always have very good consistency with the lattice calculation. So these two are basically the same, and this is our extraction of proton radius based on all the data, and that is all the data over here. And this one is the selection of C larger than 0.4, which is we basically get rid of this part of data. And we didn't plot the one we showed before. That is, we actually select C larger than 0.5 data, and that one actually gives you a proton radius as well. And the reason we didn't do that is that you can see that there's a huge error bracket over here for CG0, and the proton radius is proportional to CG. So actually, this plot over here actually corresponds to a very large uncertainty in the proton mass radius. And if you want to plot it here, that's basically standard close case solution plotted here. But you can see that as we move into a large C region, we get if we want to include those low C data, in principle, they give us better statistics. That is why you see those error brackets shrink and at this point. But there will be huge systematic uncertainty associated with that we did not include. So in general, I want to say that due to this limitation from this large C and T natures of this framework, if you want to extract the gravitational form factor large T, it's okay. But if you want to study the proton mass radius, you need more information, especially about the CG0. That's kind of the crucial part to get a good determination of the.
So the error bars for your extraction are just statistics? No?
It's just statistics. So well, another thing the kind of last thing I want to talk about is basically a little more thing we can think of how we can test the theory, because right now what I told you is just if you believe this expansion and just plug the expanding the formula, use a bunch of parameters to extract from experiment, and the idea is how do we know from experiment that if this expansion is working well or not? Right? There should be some prediction if we use this expanded form. That is actually there is the expanded form of the real part of constant amplitude actually has a non-trivial C dependence. That means if you plug that into your cross section, that actually predict a non-trivial C dependence of a cross section as well. Because, so to leading order, you'll find that with the approximate form we have before, that it predicts that the cross section kind of scale with C like this. So there's overall C to the -4 behavior, and this is some extra coefficient that correspond to C to the second, C squared and C to the 4th. So those three terms exist at leading orders and higher orders not there. So in principle, if the leading order approximation works well, this is a C dependence of the cross section, which should matter. And we took all the differential cross section data together. We found out indeed there are some non-trivial C dependence in our cross section. And using a very simple way to normalize it, we found that it's indeed consistent with the C to the -4th overall scaling. Let me kind of explain this plot as my last part of the talk. That is, the cross-section data generally depends on the C and T. So we need to normalize the T dependence first to talk about C dependence. Here we basically choose a very simple triple way to combine to fit all the data. So all the T dependence are basically described as triple. And then we basically get rid of that triple dependent T dependence, and we multiply all the cross-section with the C to the 4th. So if it's really scaling as C to the -4, after you rescale it with C to the 4th, it's going to be flat, and that's very consistent with our observation here. So this plot showing that all data basically close to this flat band, which basically means that the overall scaling is basically C2 and -4. That's what this plot means. But as you can see, that there could be extra C scaling which are not really distinguishable from this plot. So in that case, we really need much more C scaling data to really distinguish all the different coefficients, and the difference in those coefficients are crucial if you want to separate the A and C form factors. So you can imagine that you need at least 2 measurements to separate 2 gravitational form factors. So that's basically this plot. This is actually so this is actually a way we can try to test if this expansion is working, that it's starting to C dependence. So yeah, I guess I'll just skip this. It's a bit technical, but I want to spend the last few minutes talk about a very interesting quark analogy that is at this point we've been talking about quantity and gravitational form factors, and actually nothing stopped us from talking about the quark GPD and quark gravitational form factors. You can see that nothing we talked about before was specific for gluons. So there is actually very interesting analogy in quark cases. That is, they extract the C form factor, that is the same C coefficient we defined, but for the quark, and they instead of doing it our way, but they are using this dispersion relation. That is, they measure the real part and measure the imaginary part. That's really dispersion relation. There is a relation that you can extract the C form factor from that. And actually, my previous slide here actually shows that these two frameworks are kind of equivalent. So, however, the idea is that you can see that this is this extracted the so-called dispersion. The so-called pressure plot of a quark in the nucleon based on the C form factor they extract. However, the question is that how reliable, what is systematic in this extraction, right? So there has been another follow-up work by Konritsky. Actually, they show that they are trying to discuss the measurability of the pressure distribution using this framework, and those different bands basically stand for different way of extracting them. And you can see that this is the right plot is a real part of complement amplitude, and you can see that things kind of very different a lot when skewness is small, but kind of agrees as skewness gets larger. That means different extraction methods start to converge. So this actually, even though it's a very different framework, but you can see that as C gets larger, it seems to be more consistent that you can extract those gravitational form factors from the real part of complement amplitude. So this is very interesting analogy in the quark, but again, this C is not very small, so this does not mean extending our arguments here, but this is just a very interesting cross checking here for the quark cases. So with that, I will just summary here. I will talk about this exclusive quarkonium production, and I also talk about this relation between the complement form factors and gravitational form factors, the large skewness, and also use this as example. Use the JPSI production example to study the extraction of the gravitational form factor in the proton, and again, next in order evolution could next in order correction in a strong coupling, and NRQCD could be very important to this, and also there are the very interesting relation to the quark GPD. That is, can we do this, for instance, in a very similar time-like content scattering for quark cases? And also there are other relation to other frameworks. That is, for instance, the collinear NRQCD acceleration and stuff like that. So with that, I'd like to thank you for your attention.
Thank you very much. That was a very nice and interesting seminar. Questions?
How do you actually do? I mean, this is a theoretical exercise. Talking about quark GPD is just a theoretical exercise, right? Experimentally, you cannot really isolate quark and do that.
Well, there's this process called time-like content scattering, which is basically you have a real photon here, and you produce a virtual photon in the final state.
Yeah.
That's very similar to this JPSI production, except that the JPSI here is a bound state. So you see the peak, and for the time-like content scattering, you see a lepton pair. So you will see.
No, I'm not talking about the end. So you want to look at the quark content scattering.
Right. If for the TCS, that's going to be the quark GPD that's contributed. Because if there's the photo production, then the leading contribution is from quark, that is handback diagrams. I'm not sure if I had a plot of these.
You can draw it here in the board.
Yeah, it's basically like this. Without this gluon interaction.
Yeah, but these. So what kind of that's kind of like instead of a JPSI, you're talking about the light.
Yeah, a lepton pair production in the finest.
Lepton pair.
Mm-hmm.
That's a question.
Dimitra, go ahead.
Hi, thanks very much for the really nice talk. I had a couple of questions. So can you go forward a bit on the slides? Maybe it was around like 30 or so. Oh, sorry, 28.
Okay.
Yes. So I had a question about, so this fit, I remember there was recently a Nature paper where they used exactly the same data using this approach. And I remember that the error bar for CG was much smaller. Can you comment on that?
Yes, yeah, sorry, I should have put them in the backup slide. That is, you can take this reference over here. We actually performed 3 analyses. One of them is not cutting all the data here. One of them is cutting all the data with C less than 0.4. And one of them is cutting all the data with C less than 0.5.
She doesn't see what data you want to cut. You have to.
Sorry, yeah.
Use your mouse.
Yeah.
With the mouse.
You can, there's analysis that we cut all the data with C less than 0.5. That is, we cut all the data in this region. You see all this C line, right? And there's another analysis we cut all the data with C less than 0.5, so we cut through this line. So those have different statistics. And the idea is that here we only present the one with C larger than 0.5, which is the one that cut most of data. So by inclusion of those lower C data, they have a better statistics, but the problem is the systematic uncertainty will be much larger. So I tend not to put that here just to avoid any.
Okay, but I guess besides the larger bar in C, I remember that AG was also much less steep than the lattice data in the Nature paper. Was that also because of that?
Yes. It's something I don't know how to explain. That is, by inclusion of low C data, it actually agree with the lattice better, which is not something not something expected because there's large systematics.
Okay, I maybe I'm a bit confused, but I thought that there was something about a factor of 1/2.
Yes, this is a renewed version. We correct the factor of 2.
I see. Okay, that makes more sense. Thanks. And I also had can you go maybe to, I think it's maybe the one with the radii?
Yes.
Yeah. Maybe can you, I thought that there's also some extra terms in those radii, but maybe I'm wrong. Maybe for the gluon contribution.
Extra terms, yes. Those are for the summing over quarks and gluon. Okay, that's a good point. The plot I show is for gluon radii. The equation I show is for the combined radii. If you care about only quarks and gluon, there will be a contribution from the C bar, which, as I said, I didn't emphasize too much in this talk. That is, the quark and gluon also have a C bar contribution, but if you add them, they vanish. So,
but wouldn't you also have a contribution from BG and AG at 0?
The BG, I don't think it contributes to a radii, but we generally take it to be 0 because BG is measured to be up. According to lattice calculation, the BG is 0, so it's very small. So we basically ignore all the BG in the analysis. But even if it's non-zero, I think I'm not sure if it shows up in the radii. Probably yes. Yeah, I need to check it.
Okay, thank you very much.
Thank you.
More questions? I have a quick question. So if with EIC, what region of this space will it cover? Will it help you?
Yeah, I think I haven't looked at it carefully. The idea is that you kind of don't want to waste the EIC to do J-site production. I think the key you can do is to do Yuxun production, which will give you much higher masses and suppression of high order effects. And I think the general challenge in that is with the EIC, you don't get very close to a threshold. I think there is some simulation for doing Yuxun production that it doesn't go very close to the threshold of Yuxun. So that means that you don't get very large C. But I think for Yuxun, you still got a very similar C sizes as what we have here with the JLab. But the Yuxun mass is much larger, so that suppresses other kinds of system effects.
I'm sorry, why do you have to be threshold? Because you want to only look at the exclusive process, right? Why do you have to be at the threshold?
Yes.
Tell me something?
In our discussion here, we rely on the large momentum transfer and large skewness here, because the idea is that only when the momentum transfer is in one direction, you get a kind of parton exchange. That the parton is moving in that direction.
Yeah.
And the idea is that you can think of a photo production in this region that our factorization or the likelihood probably doesn't really show up in our calculation. So in principle, we want to keep here so that all this part, you see all this hard parton exchange. In this region, it's more complicated. It could be contributions. I'm not sure if it generally applies to this region. Could be that.
But this diagram you show, this watch common scattering, it does not have to be at the threshold. It's just because the cross section becomes smaller if you're not.
Yeah, the idea that when there is the hard momentum, or when there is a larger momentum transfer, this gluon exchange is approximated by it's leading to a two gluon exchange. But if it's collinear, there is no hard momentum, there is no large momentum transfer, and in the case of real, like the real photon production, there could be multiple gluon exchange, and we don't in general know what's.
So now, so where do you want to measure on your curve ideally? Oh, right, you have the curve right here. Yeah.
Ideally, well, chip size probably not. Okay,
For the
let's
chip
forget
size.
about the budget. I could talk about Upsilon.
Yes.
Yeah, well, for chip size, because there's a chip size not very heavy, it's just 3G.
That's okay. I give you the
Yeah.
epsilon. Okay.
Yeah.
And I give you the machine you want.
Oh yeah.
All right. So
Yeah, the idea is that for Upsilon, this number will be probably 0.8 or something.
all right, fine.
Yeah, you can basically measure along this line, larger than 0.5, and you will get all the see larger than 0.5 data, larger than 0.8 data, and you can probably go a little bit below.
No, if larger than 0.8, and you want to go along the line, or you want to be always at the threshold? I mean, that's what I didn't get.
Yeah, the idea is that we want to measure the full C and T dependence. The T dependency is basically what we can use to constrain the form factors at different momentum transfer.
Okay.
The C dependency is what we can use to separate different form factors and to justify the start to C expansion. So basically, at each T, we want to know some kind of C dependence in this direction.
All right.
That will give us a full two-dimensional
Okay.
information.
And but at large T's, right? Because at low T's, you don't know what you're doing.
Yeah.
Okay. Good.
Okay, any last question? No, otherwise, yeah, thank you very much.
So what is this C? This is what is the some kinematics? What is that? It's,
Skewness.
Yeah,
That's right.
I know what skewness is in terms of distributions, but not in terms of this stuff.